Alright, let's say you were asked to balance this reaction. What you're actually being asked to do is make sure that we have equal numbers of each element on each side of the process. Sometimes it's helpful not to think of these so much as elements, but to just think of them as objects that need to be counted. So what I'm going to show you is an approach that you can use so that you can more easily count the elements on each side and therefore balance your process. The lines here in front of each of these molecules or compounds is what we're going to be putting numbers on so that we can balance the reaction. So let's see how we might go about this. So you've got the K here, there's 1 here, and over here there's 1K. So we're not going to do anything about balancing that just yet. We've got a Cl here, we've got a 1Cl over here, so those are balanced as well. We've got an oxygen here, we've got 1 oxygen here, so that's okay. Now we get to the nitrogen. Now you can see we've got NH3. Now what I'm going to ask you to do is consider this as being like a box. And in that box we have 1 N and 3 hydrogens. Over here we've got N2. As you can see, we've got 1 nitrogen here and 2 nitrogens here. I'm going to treat this like a box as well. A box that contains an N and an N. Now I'm not interested in how these bond together. I'm just interested in what happens to be in each, what I'm calling a box. So what I'm aiming to do here is try and make it so we have the same number of nitrogens on each side of this reaction arrow. Here we've got 1 nitrogen, here we've got 2. So the way I can fix this so we have the right number of nitrogens is to put a 2 here. Now the 2 indicates how many of these NH3s we have. If you like, you can think about it as being 2 boxes, each containing 1 N and 3 H's. So now you can see we've got equal numbers of nitrogens on each side of the reaction arrow. We've got 1 here and then 1 here, 1 here and 1 here. Now that gives us a total of, if you count up the hydrogens now, 1, 2, 3, 4, 5, 6. And if you look, you'll see it's really just 2 times 3, but this is the reason, is because we've got these 2 boxes that each contain 1 N and 3 H's. Over on this side, we've just got H2O, so just 2 hydrogens. And if I wanted to represent that as a box, it would look like this. H, H, and O. Now my next mission is to make the hydrogens equal on each side. So as I said, I've got 6 here, but I've only got 2 over here. The way I can fix this is to have 3 boxes containing 2 H's and an O. That will give us 6 hydrogens. And 3 boxes here would mean I put a 3 in front of here like this. So as you can see, 3 times 2 would equal 6 as well. Now that gives us, if you count here, 1, 2, 3 oxygens. But on this side we've just got the 1 oxygen. In order to make this have 3 oxygens, I'm going to need 3 boxes that contain 1K, 1Cl, and 1O. 1K, 1Cl, and 1O. That gives us 3 oxygens. That matches the 3 oxygens over here. Now that means that we've got 3 Ks and 3 Cls over here. So I'm hoping you can see, that means we put a 3 in front of here. Hopefully you can see that that would mean that we would need 3 boxes of K and Cl over here to match what we did over here. So now we've got 3 Ks, 3 Cls, 3 Ks, 3 Cls. Now we put a 3 in front of here. And now that reaction is balanced. Now in front of the N2 we could put a 1 if we wanted, but generally if there is just only one of these, we don't usually put anything in front of the one that only has 1 in front of it.